Right? Today, Ramon will tell us about extremals of Khovanskii-Teissier.
All right, thank you, Jun. So before I start, I'll start with two apologies. The apology is that I usually try to give kind of non-technical talks and talk a lot about the history of the problem and the context, but I've already given some talks about this here. So I think today I have 2 hours. I'll actually go into some details and try to prove some stuff. So I hope it will be still be interesting. My other bigger apology is that I had to choose a setting, though I'm mostly coming from convex geometry in this topic. I had to choose a setting to talk in, and I decided that given the interest of the special year, it would be maybe best to do everything in a kind of algebraic geometry setting, which has connections with what people are doing here. Of course, the fatal problem with this is that I don't know anything about algebraic geometry. So I'm nonetheless, I assume this is a friendly audience, so I'm nonetheless going to attempt it. So anytime I say something about algebraic geometry, you can assume I don't know what I'm talking about. But as you will see, actually, at the end of the day, I'm going to do a bunch of linear algebra, and I hope that it'll be clear that's also a reason why we expect the kind of phenomena I'm going to show you to be kind of quite general and robust and to appear in different areas. So, but anyway, please feel free to correct me anytime when I say something stupid. So, okay, I've been told this board doesn't actually work, so I'm going to start over here. So our basic setting is going to be X is going to be a smooth projective variety, complex, complex numbers, and we're going to be interested in divisors. So I'm going to introduce this standard object, the nontrivial class, which is just divisors modulo numerical equivalent. So I'm always working with divisors with real coefficients. So this is a finite dimensional real vector space. And we're going to fix some n-2. I should have written the dimension, so that I'm going to take the dimension to be n. Okay, so we're in an n-dimensional space, and I'm going to fix n-2. You will see why n-2. I'm going to fix n-2 of these divisor classes. And now if we fix these classes, then I can define a quadratic form, Q, on n1x. The quadratic form of two divisor classes is just the intersection number alpha dot beta of gamma 1, gamma n minus 2. So this is an intersection product of n divisors, so it's just a number, right? The real number. So this defines a quadratic form on this real quadratic form on this finite dimensional vector space. And we're interested in the properties of this form. And of course, this form is very well known to everybody here. So we have this theorem, which assumes, now I'm going to assume that these divisors, so assumes that these n-2 divisors that I've used to fix the quadratic form are ample. Then we have two key properties. The first one is that this quadratic form is non-degenerate. Second, we have that this quadratic form is log-concave, which means that Q alpha beta squared greater or equal Q alpha alpha times Q alpha beta. Beta beta, thank you. For all divisors alpha and beta, such that Q beta beta is possible.
I think you could get rid of the assumption that Q beta beta became positive.
No, you cannot. I did not assume that they are ample.
Oh,
You see, these are arbitrary divisors, not ample.
but if Q beta beta is 0 or negative, then but you don't.
Q beta beta is negative. It's not
alpha might be.
Yeah, exactly. So Q beta beta has to be non-negative. You can make it strictly 0, but then everything is trivial. Okay, so Yeah, I would like to always keep it positive. The extension to when q beta beta is 0 should be. All right. So, of course, these are nothing else than the Hard-Lefschetz theorem in degree 1 and the Hodge-Riemann relation in degree 1, except that it's not the original one, right? Because normally in the Hodge-Riemann and Hard-Lefschetz theorems, all of these gammas are the same, right? And here they're different. So it's like the mixed version of these properties. And I don't really know the history of this, but this inequality over here, this Hodge-Riemann, this mixed version of Hodge-Riemann, is usually referred to as the Khovanskii-Teissier Inequality, which is the title of my talk. And it was realized in the 1970s independently by Khovanskii and Teissier that this inequality is true, and it's the algebraic geometry analog of the Alexandrov-Fenchel inequality in convex Xiao. And in fact, if you restrict this to a toric variety, then you exactly recover the Alexandrov-Fenchel inequality for lattice polytope. Okay, so now the basic question I want to talk about is, when do we have equality in this log-concavity inequality? So big theme nowadays is that we understand that these kind of inequalities over here are kind of lie underneath lots of log-concavity phenomena we see all over the place. And we might want to understand when you have equality here. And so for example, one motivation might be if you use these inequalities to show that certain sequences are log-concave, this will allow you to characterize geometric progression in these sequences. A different way of thinking about it is that if you think about these inequalities as giving you log-concavity, then objects that achieve equality really lie on the edge of log-concavity, right? So you may want to characterize what the objects lie in the boundary of the set of objects that give you log-concavity. And then that's the question. Well, this question is very old, but I'll get back to it briefly later, and then I'll talk about it. So let's answer this question, okay? Because this question has a very simple answer. So I will need a very simple lemma. So the lemma says that under the same assumption, then the following are equivalent. First of all, we have equality in this inequality. And so I'm taking here the example, I'm taking q beta beta positive, then equivalent. So we have equality. Secondly, we have that alpha minus some constant times beta is in the kernel of this quadratic form Q. Just to spell it out, I'll spell it out now. For some specific C, this C is the number Q alpha beta divided by Q beta beta. And the third equivalent condition is that alpha minus C beta is in kernel of this quadratic form for some C. And what I mean by the kernel is exactly what you mean by the kernel of a quadratic form, right? So this quadratic form defines some matrix, and it means that you're in the kernel of that matrix. So I'll just write it underneath, right? So alpha in the kernel of Q. Right? This is nothing else than saying that no matter what you plug in here, if you plug in alpha, you get 0, right? Which is the same if you translate it. If you look at what this form is, it's just saying that alpha dot gamma 1 dot so gamma n minus 2 is 0. Good? So notice there are only n minus 1 guys. So, I mean, this lemma is kind of a trivial lemma because this is just a lemma about hyperbolic quadratic forms. It has nothing to do with anything. Just so we're on the same page, let me give you proof. So, what you should notice is let's me define a new quadratic form. So I'm going to now fix beta. I'm going to just fix beta here and just view this inequality as a function of alpha. Okay? So I can define a new quadratic form. Q tilde alpha alpha, which is just the deficit in that inequality. right? So this is a quadratic form as a function of alpha, right? And the Khovanskii-Teissier inequality says that this is a positive semi-definite quadratic form. Right? And now what we said over here in part one is we said that this Q tilde of alpha alpha equals 0. So this condition 1 over there is just saying that Q tilde alpha alpha equals 0. Right? But if I have a positive semi-definite quadratic form and I have an element at which it attains 0, that element must be in the kernel. So that means that alpha is in the kernel of this Q tilde. And if you just check what this means, this is just equivalent condition. I've just written out over here what it means for alpha to be in the kernel of this Q. Just check it. It's just it's exactly what it is. And now, of course, 1 and 2 are equivalent. 2 implies 3. That's obvious. And why does 3 imply 2? Well, if this is true for any constant, just multiply this with alpha minus c beta. Just multiply it by beta. And then you will see that you can just solve for c, and c must be this. Okay, so that's it. So then 3 implies 2 is. That's the. Yeah.
But under your assumption, because you're assuming they're ample, Q is not generate.
Good. So that's the next step. All right. So note that I didn't use anywhere in this lemma that they are ample, right? All I used is that this inequality over here is true. Right? But indeed, the point is now that by the Lecture's theorem, our Lecture's theorem implies that if you have equality, if and only if, right, alpha minus a constant times beta is in the kernel of Q, but the kernel of Q is trivial, right? Which means that alpha and beta are proportional. Something. In other words, the inequality is always strict, except in trivial situations. Good. We're good? There's no interesting equality cases of the Hodgkin relation. That's what we said. Now I spent 10 minutes or something explaining this to you, and now we're done, right? So we can, the remaining 1 hour and 50 minutes, we can do something else. Now, of course, this is not the real problem, right? So, all right. Let's see, I don't need much. I can try to, I won't need what's written on this one. It's okay. So fast I can get. So what's going on here? So this board over here, the one that's soon to be covered up, is narrow severing space. Okay. And in this space, there's a cone, which is the cone of ample divisors. And if we take gamma 1 to gamma n minus 2 in this cone, right, then we have no interesting equality cases. But this cone is open. Okay? This is an open cone. So if you take its closure, the closure of this cone, this is called the Neff cone. So there are elements that lie in the boundary of this cone that are not ample, right? They're Neff. And of course, any Neff element is a limit of these ample elements. Now I don't need this thing can fall down. Okay? So you see, if you look over here, I have here an inequality for when gamma 1 to gamma n minus 2 are ample, right? But these intersection products are continuous. So I can just take the limit of this inequality, and this inequality remains valid when these guys are just Neff. Right? Now, in this proof of this lemma 1, I never use the fact that they're ample, right? All I use is that this inequality is true, right? So this lemma 1 also remains valid when these gamma 1 to gamma n minus 2 are nif, right? On the other hand, this Hard-Lefschetz theorem absolutely fails if you replace gamma 1 to gamma n minus 2 by nef elements. There's no reason why if I take a limit of a sequence of non-degenerate quadratic forms, I should get a non-degenerate quadratic form, right? In the limit, I can get some element in the kernel that didn't exist before. Does that make sense? So the real question is, when do you have equality in the homogeneous relation or in the Khovanskii-Teissier inequality? When you don't have ample, devices here, but you have nef. That's the real question that we want to ask. And you see, this lemma is still true, but the Hard-Lefschetz theorem is no longer true. In particular, you can just reformulate this. Which is that we want to characterize the kernel of this quadratic form when gamma 1 to gamma n minus 2 are in. So in a sense, if you want to put it this way, the question is, what is the correct replacement of the Hard-Lefschetz theorem when you have nef n? This Hard-Lefschetz theorem degree 1. What's the correct replacement when the gamma 1 to gamma n minus 2 are in? It's no longer non-degenerate, so it may have a non-trivial necessarily. It could be. So it may have a non-trivial kernel. So what is that kernel, right? That's what we would like to understand. Everything clear? Now, maybe this is a good moment to make a tangential remark, which is that I'm always talking here about this degree 1, Riemann and Hard-Lefschetz. Of course, this second question I asked, you can also ask it in any degree, right? The problem that what you have in higher degrees is that when you go to higher degrees, the correct analog of the Hodginian relation higher degree, even the inequality is no longer true if you replace the ample elements by Shenfeld. As a counterexample in one of my papers. So if the inequality isn't even true, of course, you can still ask about understanding the kernel, but we use the inequality everywhere. Okay, so if even the inequality isn't even true, then it should be much, much harder to understand what happens to the kernels of these elements. Okay, so I'm not going to touch on that at all, right? So we're working here in degree 1, where at least the inequality extends by continuity to the boundary of the element. Okay, and otherwise you really have a different picture, I think, of what is going on. Good. So now let me just very briefly say something about the history. So in the toric setting, this question is very old. It dates back to Minkowski. And Alexandrov. This is just asking about the equality cases of the Alexandrov-Fenchel inequality for polytopes, right? Because if you have a toric variety, these intersection numbers just become the mixed volumes of polytopes, and this translates to a question in convex geometry. And I gave a colloquium some time ago where I explained kind of the history and how Minkowski thought about these kind of problems. I'm not going to repeat them. But this case was completely settled. By Shenfeld and myself some years ago, and that's what I'm going to talk about is based on that. So meaning that whenever gamma 1 to gamma n minus in the toric, for if you have a toric variety, if these are any nef divisors, arbitrary, we have a complete characterization of this kernel of Q. So the problem is completely solved in that case. Now, in the more general setting, so let's say in the algebraic geometry setting, I don't know how to call it, non-toric setting, I don't really exactly understand. I mean, I've seen in the literature that people attribute the same problem or related problems to Teissier. I went back and I read those papers that they cite, and I couldn't find exactly this problem formulated there. But it's clearly somehow the idea of understanding something about these boundary cases was certainly there. I also saw some reference to Simonyi, but here there wasn't even a paper cited when just Simonyi asked this question. No, I never met the gentleman. But in any case, it seems that kind of similar questions were asked. I don't know how important they were considered. You know, it was unlike in this case where these are very fundamental questions. You will find in most textbooks on the subject. But after we solved the toric setting, this was taken up by Hu and Xiao, and they kind of extended the techniques that we have over here to more general varieties. And they did not manage to completely settle the problem. In fact, there are vast numbers of open cases, but let's say there are partial results. So they proved some partial results in this direction based on the technology that they were facing. The other thing that they did is they actually really clarified what you should conjecture, which entirely obvious. So there are these two papers, and somehow what I'm going to be talking about is based on these.
If I assume they're conjectures,
Yes.
how easy it is to recover your result, Shenfeld, in the toric setting?
Well, the conjectures literally translate
the
back
same
word for word. Yes. So I will show you. Okay, I will write down some main. Yeah, they literally translate back word for word. There is some subtlety in how exactly to formulate it in the. But we somehow believe that the things that we prove in the toric setting should be very robust and very general in some way. And so far, there's only a limited number of situations. I mean, there's no situation where they've been completely understood, except on the complex torics. That's a different story. But that's much simpler situation. Okay.
So the reason why we cannot prove Hu Xiao's conjecture is we are not good enough at linear algebra, or we are not good enough at algebraic geometry.
You're not good enough at algebraic geometry. So one of my aims is to try to at least give some hint about where the obstructions lie, but I don't know how far I'm going to get, but I'm going to do it. So what my goal is in this talk is to prove the simplest case, that the simplest non-trivial case of this result here, which I'm going to do literally by copying the proof that's over here, okay? With some, hand waving about algebraic geometry line. Okay? So that's my aim. We'll see how far I get. So let me write down the statement. So the simplest non-trivial case is when gamma 1 to gamma n minus 2 are net and big. Big, meaning they have positive log. And this is a hugely simplifying assumption. Right, so this just means that right, gamma is big if gamma to the power n is positive. Okay? Good. So here's a theorem. Let me call it main theorem of this talk. So this is in the toric setting, this is a very special case of our theorem. And in the algebraic geometry setting, this is a special case, but not a very special case of the results of Hu and Xiao. So let's assume this. A nef and big. And we assume as usual that Q beta is positive. And the following are equivalent. First, that we have equality. Here's the key point. So this is equivalent to alpha minus a constant times beta for some constant being in the kernel of Q. So I have to characterize the kernel of Q, right? So that's going to be the statement here. The statement that it's going to be, you know what, let me eliminate this beta. This beta is annoying. So I'm just going to directly work with the kernel of Q. Okay, so it's the same statement, right, by this lemma one. So what's equivalent is that alpha is in the kernel of Q. The statement, second thing is that alpha is in the linear span of the prime divisor classes that are in the kernel of Q. I just mean, well, I could have just written that the kernel of Q. Good. So if gamma 1 to gamma n to an f and b, this is the state. Good. Now it looks kind of self-referential, right? Because I have kernel of Q on both sides. So what I want to, what I want to do for probably the rest of the first hour is not yet to prove this theorem, but to try to convince you that this is really a combinatorial characterization. Okay, so this is a meaningful characterization. Well, I mean, it's a simplification in itself, but my claim is that checking whether a prime divisor is in the kernel of Q is something you can just do. That's a combinatorial property. Whereas checking that a general divisor, alpha, is in the kernel of Q, this requires you to check some kind of cancellation, like we don't know how to do that. Right? That's about numbers. And this is a combinatorial condition. So let me try to explain this first.
How should we read this, the toric setting for like convex polytopes?
I will show you.
What is it saying?
I will show you. Let me explain it. So in the convex setting, I will explain it now, but in the convex setting, this is just saying something about the dimensions of the faces of the polytopes gamma 1 to gamma n minus 2. So it's a statement about dimensions. And so it doesn't have to do with what polytopes there are, how high are their facets, what exactly is their support function. It only has to do with the dimensions of the faces. And that's what I really mean by it's a combinatorial property. This condition for a prime divisor is a combinatorial property. You call dimensions combinatorial, but it's not numerical, right? It doesn't have to do with the values of the support function. Does that make sense? So that's what I mean when I say combinatorial in this. And I will try to explain that exactly the same thing is true in the general setting, in the algebraic geometry setting, if you give me a notion of dimension that's well adapted to this kind of business. So the point is that this, for a prime divisor, checking whether this is a combinatorial. Okay, so let me explain this. So the first point, what does it mean for a prime divisor to be the kernel of Q? This just means that this intersection number, I've just written the definition of what it means to be in the kernel of Q, right? Now, before maybe I take a slight detour because I need a little property which I will use many times. So maybe I'll get it out of the way first. It's a kind of trivial property. Which is that if I take some nef, let me now take n minus 1 of them, right? No, let me do this later. Where do I want to go? let me put it this way. What is this object over here, right? I'm taking a section of a prime divisor. So really all I'm doing is I'm taking each of these divisors and I'm restricting them to this D, right? It's an irreducible subvariety, right? I'm restricting each of the divisors to this D. You have to worry a little bit about whether some of these divisors have D in their support, but because these are classes, you can just move them a little bit, right? You can move to a linearly equivalent class where you don't have D in the support, and then you're good, right? So you can restrict each of these divisors to D, right? So this is really just saying that gamma 1 restricted to D is 0. Does that make sense? And this is just an intersection number. These are again Neff divisors, right? So this is just the intersection number of Neff divisors. But this is saying that the intersection number is 0. Okay? So this just means that basically some varieties don't intersect. So that already suggests that's a very qualitative condition. That's not a numerical condition. It doesn't have to do with the coefficients of these gammas. Now, in order to really understand this story, I need a little detour. So we need to understand when are intersection numbers of Neff divisors 0. So let me not work on D, let me work in the full space to develop this. Suppose that gamma 1 to gamma n are Neff. Now I have n of them, not n minus 2. So then it's always true that their intersection number is not negative. So you might ask, when is it 0? So if I have n Neff divisors in n dimension, I take the intersection number, it's a non-negative number. When is it 0, right? So when do they not have intersection? Now, this should be a standard fact, I think, but it's kind of hard to find in literature. But in the convex geometry literature, this is just a statement about when a mixed volume of polytopes is 0. And it's a completely standard fact you find in any textbook in convex geometry. And the statement literally translates to the algebraic geometry set. In order to do it, I need to introduce the following definition. If I take a Neff divisor, then I'll define its dimension to be the maximum number k such that gamma to the k is not equal to. So this is called the numerical dimension of the divisor. Now in the convex geometry, so in the toric setting, and so any Neff divisor corresponds to a polytope. And this dimension of gamma turns out to be exactly the dimension of this polytope in the usual sense of convex geometry, right? So if I have a polytope with non-empty interior, the dimension will be n, right? If I have, let's say, an n minus polytope living in an n minus 1 dimensional space, the dimension will be n minus 1, etc. So this definition literally extends the definition of a dimension of a polytope in the usual sense that we all understand to the Neff device. So also just a remark for future reference is that by definition, gamma being big is just the same as saying that gamma is full limit. And so this is just a translation of the condition I gave there to the setting of the Alexandrov-Fenchel inequality. Right? In the Alexandrov-Fenchel inequality, that would just mean that the reference polytopes are full. All right, so no, I want to keep this up. So let me give a characterization of when intersections are 0. So this is an n dimension. No. I want another. The other remark, which I'm going to use many times, is that if gamma is Neff, then gamma to the k is 0. So if gamma is Neff and omega is ample, So any ample class, you can pick whichever one you want. Gamma to the k is 0 is the same as saying that this number, gamma to the k, omega to the n minus k is. But you can just multiply it by any ample class to get a number. And if that's 0, this is not a number, but that is a number. That's 0, that's equivalent. Okay. Is it obvious? Should I prove it? I mean, so the point is that so you see, I mean, gamma might lie somewhere over here, but omega lies in the interior, right? It lies in the ample cone, it's open, right? So because omega is open, omega plus t delta is also ample. For any divisor, and t is sufficiently small. And the ample cone is open, so I can perturb omega in every direction, right? And I still be in the ample cone. So you see, this is always not this for any omega here, this is always non-negative. Sorry, for any gamma, this is non-negative. Right? But it's 0 at omega, but if I perturb omega, right? So I fixed omega. I just know for omega this is 0. But for any omega, this is non-negative. Right? So this minimizes, right? This is saying that that particular ample class minimizes gamma to the k omega prime to the n minus k. So I can just differentiate because of this property. I can just differentiate with respect to omega. That means I can replace omega by any other omega. And I just keep doing this, right? So just by differentiating this property, I can just, if I have this for an ample class, because they lie in the interior of the, or lie in the ample cone, which is open, I can just differentiate this n minus k time and say that gamma k omega to n minus k for any omega, for just one specific omega means it's true for all omega, gamma to the k omega 1 through omega n minus k equals 0, and then you basically have the definition of numerical equivalent, right? So that's the kind of perturbation argument you should have.
I mean, you're assuming that it's sort of generating degree 1.
Yes, that's true on a smooth projective variety, no?
No.
Then we have a problem.
Yeah, I mean, I think what you're saying is true, but it's harder than what you're saying.
So, what generates degree 1?
Homology. Like there are some like a higher degree homology classes that cannot be expressed as linear combination of monomials in divisor classes.
But I'm working here with gamma to the k, right? I'm not working here with some arbitrary.
But if you went from gamma to the k is 0, you need to multiply it by everything in complementary degree and check it's 0. It's not enough to multiply by.
So you probably need an extra argument here, but
what you wrote is fine.
yeah, I think. In a sense, you see, I never defined these other higher degree cycle spaces, right? So when I say something like this, what I really mean when I write this, which maybe is not, okay, I never said where this object lives. But because at the end, we're always going to the highest degree, right? What I really mean by gamma to the k equals 0 is that if I take gamma to the k and multiply this by n to the n minus k, anything else, any other divisors, I get 0, right? That's what I mean. So that's the only notion in which I'm going to use this identity. So if you accept this as a definition of this object, then what I said is true by definition. And you are using a different notion of what it means for this to be equal to 0, which would require then an extra step in the proof, which I don't know how to do. But presumably you guys know it, so that's good. Good enough?
How is this dimension related to the Yutaka dimension?
I have no idea, but it's a lot of been written about it.
It's the same thing.
It's the same thing, right?
I mean,
It's
if
just
you
the
assume
dimension
F
of
and D.
There's a paper by Lehman. It's called Comparing Numerical Dimensions. He has like a list. Yes. But this is actually not for NEF. That's for more general than NEF. So I think that makes it harder. I'm only talking about this in the case of NEF, which should be much easier. But I'm going to use this a lot because it allows me just to reason about numbers. So, and we'll use this argument again. Okay, so here's a lemma. It's called lemma 2. So suppose gamma n to gamma n, gamma 1 to gamma n is net. And the following are equivalent. First is that the intersection number is 0. And here's the condition, which is literally just copied from the convex geometry setting, which is that there exists some indices, some k, and some distinct indices I1 to ik from 1 to n, such that the dimension of gamma I1 plus gamma ik is less than k. For example, if you take the sum of all of these guys and their dimension is less than n, it should be obvious that this is 0. Because this guy is less, right? Because all of them are positive. So this guy is less than the sum of them to the power n. So if the sum of them to the power n is not, right, if the sum of these guys is not big, then obviously this is 0. But there can be other reasons why that is 0. You don't have to have the sum of all of them to be not big. It's enough to have k of them that sum to something of dimension less than k. And all of these cause u to be 0, and these are the only reasons why you're 0. And, you know, let's answer Jun's previous question. Let's translate this in toric setting. So in the toric setting, this is just saying that the mixed volume of n polytopes is 0 if and only if there exists a k and distinct indices such that the dimension of the sum of these polytopes is less than k. So just saying something about the dimensions of the subspaces in which these guys live, or about the relative position, because I have to be able to take sums of them, right? So if this guy lives in one subspace and that's in the other, this is the linear span of the subspaces in which they live. So this is some kind of condition about the dimensions of a bunch of subspaces. But this is what I mean when I say a combinatorial condition. It doesn't have to do with exactly what these polytopes are. What is where do the supporting hyperplanes lie? It only has to do with their dimension.
So for polytopes, that condition turns out to be the same thing as being able to find line segments.
Yes.
Is there something like that can I find?
It is an interesting question, very much related to something that I may or may not get around to later. However, literally speaking, the answer is no, at least in the same sense as polytopes. Because for polytopes, it means that there exist line segments, right, which are themselves, these are polytopes of one dimension, right, that lie inside these guys, right? But if I have a toric variety, imagine you have a fan with the property that given any hyperplane, it cuts one of the cones of the fan. Most fans look like this. Then this fan will not contain the divisor, so the toric variety, right, will not have any one-dimensional divisor. Because a one-dimensional divisor, its support function has to be, it has to be linear. How does the support function of a segment look? You take the hyperplane orthogonal to the segment, and it's linear above and it's linear below. Right?
So I think the subtlety is like in interpreting the question, like what does it mean for one polytope to be contained in the other, and how to translate that into geometric setup. It's not clear, like if you give me gamma 1 and gamma 2,
Okay.
what does it mean to gamma 1 to be contained?
Containment is not the problem here, because it's not about containment. It's just a containment of the subspaces in which they live. But it has nothing to do with it doesn't have to be in P1, because everything here is scale invariant. It just has to do with the subspace, right? The linear subspace of the line has to lie inside of this. And if you want to say that, you can just say that if let's say you have a polytope P of dimension K, and you want to say that Q lies in let's say in some translate of the affine hull of P, then you just have to assume that dimension of P plus Q is equal, right? The problem is that we want Q to have dimension 1, but in a toric variety, it doesn't need to be that there are any divisors of dimension. So you may have to blow up the, right? And then, I don't know, right? I mean, On the toric variety, I can just cook something up, but we don't know when, or I don't know anyway, whether this even makes sense in a, right? If I give you a projective variety, you would now have to blow up so that you get some divisors of dimension 1 that have good properties. And this is very closely related to the reasons why we don't know how to prove that theorem in outside of convex geometry.
I think the question makes sense. I think it's an interesting question.
I think the question is not only makes sense, but has it's a simplified form of the kind of general problems we have in translating the proofs that we have in convex geometry to algebraic.
Because the condition 1 on saying that something is 0 is like a birational property. You can check it on any birational model.
Yes.
You don't have to live inside.
Exactly. But you have to, so yes, so you're allowed to blow up, right? But you have to construct these blow-ups so that you now have some nef elements of numerical dimension 1 in the blow-up that have certain properties. And we simply, you know, I've discussed this with various people and it's not clear how to do that. But if I have time, I will come back to this. But this is very, I mean, we exploit this also very in the Alexandrov-Fenchel setting to prove the complete equality cases. We exploit this property much more heavily than over here. And the absence of such a thing in general, or that we don't know how to construct it, that's one, you know, that one, if you really wanted to translate the proof in the convex geometry setting completely, you would need something like this. So either you have to develop something like this or find a different way to, right? And so far, neither of these has completely settled. But this is a very natural question, and it's a very important question as well. I don't know if it's important for algebraic geometries, but I think it's it lies deep in the problems that we. Would you like me to prove this lemma for you? Let me do it. So let me at least start. So the nice thing about this lemma is that, so I will not actually need, I'm giving you this lemma as context, because I will need it later if I want to discuss why we can't translate things. I won't actually need this lemma in the proof of that thing. But it's a nice illustration of the kind of arguments we give, because this lemma basically only uses HR1 and this lemma over here. And that's true for all of the things I'm going to say today. They only use HR1 and this. So, right, so really as input, we don't take anything kind of deep as input, right? It's just linear algebra using those two conditions and see what you do. So the point is to prove by induction. So let's fix some ample guy. And the point is to show by induction on K that there exists some I1 equal to IK indices from 1 to n, some set I, subset of 1 to n of size greater or equal K plus L, and some L greater or equal 0 if K plus L less or equal n greater than 1, such that if I take gamma I1, gamma IK, gamma I to the L, omega n minus K minus L equals 0. Here, gamma I is just the sum. This I is a subset of indices, just the sum of those indices. So it looks a little bit nasty, but you see, when K is equal to n, what does this say? So when K is equal to n, this is just the assumption 1, right? So when K is equal to n, this is just the assumption 1. So on the other hand, when K is equal to 0, this shows that there exists a set I, right, such that the sum of the gammas with those indices I to the L times omega to the n minus L equals 0, which is exactly the conclusion, right? Because that shows that the dimension is less than K. Does that make sense? So we just want to run the induction on K, right? So every step, right, we start with something like this. I've already created L copies of this guy, and I have K of these left. I want to basically remove one of these and maybe create an extra one of these or an extra one of these. Does that make sense? Okay.
How is L quantified?
There exists some L is greater or equal than 0, and and it satisfies this property. All of this is in the for exists. Maybe I should have exchanged these two lines. There exists indices I, there exists some L, there exists, right, some L with these satisfying these two properties.
Okay,
There exists some set I of this size such that.
Okay.
Okay, so yeah, everything is in the for exists. So the basic point here is just to use the let me go. Where do I want to go? Just use HR1, so just use the Khovanskii-Teissier inequality. So let's assume for a moment that if I replace the first guy over there by gamma I, suppose L is greater than 1, all right? Otherwise, what I'm saying is not, doesn't make any sense. Suppose L is greater than 1. So I already have a gamma I. Suppose that if I replace the first guy by gamma I get something that's not 0, right? Gamma I dot gamma 2 or gamma k times gamma I to the L. Suppose that this is actually positive, right? So if I replace gamma 1 by gamma I, I'm no longer 0. Now, in this case, what we can do is we can just apply HR1, because you see, I have here, you can think of the Q over there as now being Q of gamma I1, right? And the rest of them are reference bodies. So HR1 says that 0, which is the square of the assumption, right? By assumption, this is 0, that's over there. It's greater or equal to what I get if I replace one of the gamma i's by I1 and or I1 by one of the gamma i's, right? So it's gamma I, gamma I2, gamma IK, gamma I to the L to the L. What am I doing? This one. Times what happens if I replace one of the gamma i's by a gamma I1. Which means that you see, these guys are positive, but the left-hand side is 0. So this is actually equality, right? So we actually get equality in HR1, right? On the other hand, what we assumed is that this guy is positive, right? So we can apply this lemma because we have this condition, right? I'm taking beta to be gamma I and alpha to be gamma I1, right? So what this is saying, by applying lemma 1, what we get is that we can replace one of the gamma i's, right? So we get that this is in the kernel of the quadratic form. It just says that gamma I1, gamma IK, gamma I to the L minus 1 equals 0. I've just removed one of the gamma i's. That's by this lemma 1. If that's true, I can multiply this by an omega. So what I've shown is that if it were true that if I replace gamma I1 by gamma I get something positive, then I can just replace one of the gamma i's by an omega, and I still get 0. Okay? That's the first step. So you can, of course, iterate this, right? So what we do is we keep repeating this step 1 until this is no longer true. Okay, so up to replacing some of, right, we're decreasing L and increasing here this, up to decreasing L, right? I can just keep changing gamma i's to omegas until this equals to 0. So from now on, I'm going to assume that this is equal to 0. Okay, is it good? Now in step 2, suppose there exists an L from 1 to k, such as gamma IL times gamma I2, gamma IK, L is between two gamma I to the L, omega to the, ooh, too many L's. S. Follow, right? So I play the same game now. Now I assume that I replace gamma I1 by gamma IS, where S is one of the other indices. Suppose one of these guys is positive. Then I can play exactly the same game. And what it shows is that then I get 0 if I replace the gamma IS by omega, right? So then I get that gamma I1, gamma IS minus 1, gamma IS plus 1, gamma K, omega, sorry, gamma I to the L plus 1, L, omega N minus K minus L plus 1 is 0. But now I declare victory because now I have replaced K by K minus, right? Because now I have one less of these guys, right? So now I can continue the induction. Is it good? So the only step I have left is what happens if all of these guys are 0. But if all of those guys are 0, I can just add them up, right? So there's two situations. So if L is greater or equal than 1, right? And now I've assumed that this guy is 0, right? But then I'm good, right? Because if this guy is 0, right? Then I've already achieved, I've already decreased K because this is just gamma 2 to gamma K times gamma to the L plus 1. That's omega to the N minus K minus L. Right? So I'm already done. I've already decreased K just by the contrapositive of the assumption of step 1. Now, if L equals 0, then what I know is that the contrapositive of step 2 is that for all S, gamma IS times this equals 0, right? But then I can just add up all of this thing over all S's. And then I get that gamma I dot gamma I2, gamma IK, and omega to the N minus K equals 0 for I is just the set I1 to IK. And I'm also good because I've decreased L. That's it. So you see, just by using this Khovanskii-Teissier inequality and its kind of trivial equality characterization, I can just keep replacing elements here by either an ample guy, or I can sum them all up and get another. I just keep doing it. So it's a very straightforward linear algebraic fact. Any question? So many proofs look like this, right? We keep using this inequality and its trivial equality characterization in kind of creative ways and try to see what's in it. But by the way, this statement has nothing to do with divisors. You could write something similar for Lorentzian polynomials and you would get a completely analogous. So just to end the first hour, am I supposed to have a break in the middle or can I power right on? I usually just power right on, but it depends on how tired the audience is. We'll see. So just to go back here, I just want to now make the point that all right, I just here what we want to understand is not whether the product of n Neff divisors is 0, but whether D, the class of a prime divisor, times n minus 2 Neff divisors is equal to 0. So the condition that D is in kernel of this quadratic form cube, it's the same thing as saying that D dot gamma 1. That's just the definition of the kernel of Q. By the same perturbation argument as before, I can just stick on an ample guy. It doesn't make any difference. So now I just have a number. And what is that number? This is just the intersection number. This is an n-1 dimensional subvariety, variety, and I have n-1 guys. And now I'm back at the characterization that I had before. Well, this is saying that there exists a K, which is a subset, a K, and I1, Ik, which are in the set n-2, such that the dimension what am I saying? No. Gamma I1 let's see. And then this is a kind of combinatorial condition. It just says something about the dimensions of the restrictions of these divisors to D, right? To the irreducible variety, I'm saying. Is it good? Now, to come back to June's question, what is this in the toric setting? Let's translate it. So in the toric setting, what happens is that the Néron-Severi space is generated just by the T invariant, by the toric invariance prime divisor. And they correspond to passive directions. So in the toric setting, these guys correspond to rays of the fin. And remember that a net divisor corresponds to a polytope. Not just any polytope, but it's a polytope that is compatible with this fan, right? So whose fan is a coarser than the fan of that defines the variety. And the restriction to such a prime divisor, to a toric invariant prime divisor, corresponds exactly to the face of P. So let's call this ray U with normal direction U.
But there is still something one needs to argue, because if I assume this, it's not saying that I can check just the torus invariant prime divisors. Here the statement is that you have to check all prime divisors.
But it's a span, right? So this is maybe when I give the proof it will become more evident, but
the claim is that if X is toric, then in the right hand side I can replace D prime by D torus invariant prime.
yes,
That's the claim.
yes.
But like, isn't that if you take a positive linear combination of these prime divisors and that's in the kernel, then each of the prime divisors lies in the kernel?
That's true, but why should it be positive, right? Is it true that, no, okay, so in the toric setting, this is true. Right. So in the toric setting, it's true that's right, because you add the divisor generate the what's it called? The principal divisor generated by the character, which is effective, right? So I think so. Now we're talking about stuff I don't really know.
Yeah, those are the extremal rays.
Yeah. So every in the toric, this is special to the toric, right? So every prime divisor is a positive linear combination of those toric invariant prime divisors. So it's enough to study those. In any case, when we prove this in the convex geometry setting, we don't go through this. We just directly only work with the torus invariant guys. So for example, what's true in the toric setting also is that the big cone is just the cone of all linear combinations of torus invariant prime divisors with positive coefficients. This is not something that's true in general.
Matt, are you saying that you can always just go over the extremal rays of the effective cone of divisors on the right hand side?
Well, I mean, there's you have to worry about like pseudo effective versus effective, maybe, but yes, basically. Okay.
I have to remind myself, if I take any on the toric variety, any divisor class, and I add some principal divisor generated by a character, then I can always do this and get a torus invariant one.
Positive linear combination.
Yeah, so but these are effective, right? Is that the argument you're making? Something like this.
Well, it's like D is equal, the class of D is equal to the class of
Exactly.
positive.
But now I want to argue that, okay, yeah, if I put it in, I need to if I take any, maybe I should do this. Right? This guy is linearly equivalent to a torus invariant.
Yeah.
Well, it's linear, that's what I wrote.
Yeah.
That's a linear equivalent.
So that's a positive sign.
But it's a positive.
Yes.
But anyway, I mean, I'm now getting bogged down in I'm trying to translate so there's some special things that happen on toric varieties. But the point is that at the end of the day, the characterization, what it reduces to is that take D to be torus invariant, right? So D in the kernel of Q is the same as saying that there exists, let's say, K and I1 not equal to IK, such that the dimension, so D corresponds to some normal direction U, right? So the dimension of the face of the sum of these polytopes with normal direction U is less than Q. So it's saying something about the relative positions of the subspace, the dimensions of the subspaces in which the faces of these polytopes. And that again is a combinatorial condition that you can check. I mean, if I give you a bunch of polytopes, this is a very easy thing to check. It doesn't depend on the polytopes themselves. It only depends on the spaces, right? The positions on which the spaces live in their dimensions. So this is something that in the toric setting, you can easily compute. Now, whether you can compute all of these intersection numbers over here on a general variety, I don't know. But in spirit, it's very much the same. June, I agree. There is one has to justify this passage to the torus invariant divisors. I looked at it briefly yesterday, but I didn't look at it carefully enough to give you a good answer.
One could also wonder if this would be sort of easier in the case of like homogeneous spaces where you have more control over things.
Yeah, I have no idea. So this is so you have to understand. I come from convex geometry, and everything I know about algebraic geometry is kind of by translation table. So what I find fascinating about the story is that because all of the proofs only use linear algebra, it feels like if you have the same kind of algebraic structures, then you should have the same things going through, right? But what do these things say? Also, the other question that is interesting is are there applications of these kind of theorems actually to problems in algebraic geometry? So it's not so clear that people in algebraic geometry don't seem to have really. I mean, okay, I cited Teissier and Simonyi, but it would be very interesting if one could have some settings in which this is useful, and that I don't. Unlike in convex geometry, this is a completely natural kind of question that arose from the very beginning. So these are all very good. What am I doing on time? I spent a lot of time. All right, let me not break the break, if that's okay for everybody. Power through. Because I wanted to try to prove this for you, modulo some like confusing things like we just said, and errors of algebraic geometry. So let's go back here and let's start. So what I'm going to do is I'm going to make an attempt to prove it. That is not mine. This attempt is due to Ramon Van Handel in a long time ago. Actually, I mean, I'm slightly misrepresented. So when I say that this is a failed attempt to the Hermann-Weyl wasn't trying to prove this theorem. What I'm going to show you here is a technique that's used in the classical proof of the Alexandrov-Fenchel inequality, and it dates back to this paper of Hermann-Weyl. The way that the classical proof of the Alexandrov-Fenchel inequality works is you start by everything being ample, and then you have to prove basically the hard Lefschetz theorem. And I'm kind of paraphrasing what is going on. And the technique of Hermann-Weyl is how in convex geometry people do it. Okay? So he applied it successfully to the ample case in which there are no interesting equality cases. And the question is, why can't we just repeat the proof, the classical proof of this, and use it here, right? So that's what we're going to do. So here's how it works.
Is he the one who proved hard Lefschetz in 1970?
No, there's no hard Lefschetz. Hermann-Weyl gave a simplified proof. So of the Alexandrov-Fenchel inequality in the case that all of these bodies are the same. Okay. It was originally proved by Minkowski in a completely different way. Then Hilbert found a spectral proof that we all know and love today with homotopy. But it had a very difficult part of it in having to do with elliptic differential equations. And Hermann-Weyl replaces by a very simple argument. And that very simple argument turns out to be the way that Alexandrov later was able to extend the inequality to general convex problem. Okay, so I'm repeating now this argument of Hermann-Weyl. There is no algebraic geometry here. It's all convex geometry. I'm just translating literally step by step. So remember that we're starting with an element in the kernel. So we're starting an element in the kernel. And let me just again write what this means. So this just means that what does it mean? It means that alpha dot gamma 1 or gamma n minus 2 is 0. Right? That's just what it means to be in the kernel. In particular, if I take any prime divisor, I can just stick it on and I have 0. Right? Now, what I want to do I can just think of this as the intersection numbers of these divisors restricted to D. Right? So what I would like to do is I would like to apply this HR1 to that intersection number, dimension n minus 1. Right? So I'm going to apply it where alpha is alpha and beta is this gamma 1. Is it good? So this says that this squared, which is of course also 0, if this is 0, this squared is greater or equal this with gamma 1 replaced by alpha, and this with alpha replaced by gamma 1. But all these things are big, right? So surely if I replace alpha by gamma 1, right, then this should be positive, right? Which means that the other guy should be 0. So we should get that alpha of gamma 2 and minus 2 is less or equal to 0. Good? It's not good actually, but we will see that as well. But I've just applied, right? I've just applied the HR1 with alpha is alpha and beta is gamma 1, right? On the restriction scheme. And this is true for all prime D. So in particular, we have that if I take alpha the gamma 2 to gamma n minus 2 and I multiply it by anything that is pseudo-effective, then it should be non-positive, right? Because I can just get those as the limits of the effective divisors. Let's say delta dot pseudo-effective. All right. Now, what I want to do is I'm going to choose one particular delta, which is gamma 1. Right? Gamma 1 is Neff, but certainly pseudo-effective. So but, right? Gamma 1 dot alpha dot gamma 2 minus 2 equals 0. This was true by construction because we assumed that alpha is in the kernel of Q. Right?
Don't I have too many divisors?
That's unfortunate. No. I don't think so. 2 to n minus 2, so n minus 3 of these, n minus 2, n minus 1, n. I don't have a gamma 1. Do I have too many? You see, gamma 1 disappeared because I applied Riemann with gamma 1 equals beta. Is it okay? Okay. But here I just replaced delta. I can pick any delta, so I can pick gamma 1. Any delta of 2 effects, so I can pick gamma 1, and for that it's equal to 0 because it was in the kernel. Right? Now I want to argue that gamma is big. Right? Gamma 1 is big. So it is in the interior of the pseudo-effective cone. Because the interior of the pseudo-effective cone is the big cone. That's a theorem, I suppose. I found it somewhere. For example, in the book of Lazarsfeld, such a theorem. So it's in the interior, which means that I can play the same game as I did with the ample before, right? I can wiggle it in any direction, right? So we know that for any pseudo-effective divisor, this is negative, right? But it's 0 at gamma 1. So I can wiggle now gamma 1 and replace it basically just by a perturbation argument by any other divisor. And therefore, if you agree on my convention for equality, it should be the case that alpha dot gamma 2 dot gamma n minus 2 actually equals to 0. I said that for gamma 1 this is 0. Now take gamma 1 plus t times delta, where delta is anything, right? Because it's in the interior of the pseudo-effective cone, it will still be pseudo-effective, and therefore it will be negative. For any point in the neighborhood of gamma 1, this is negative, but at gamma 1 it's 0. So gamma 1 is a maximizer. So now I just can take d dt equals 0, right? And I can replace this by any device. And therefore this is it. Is it good?
Yeah.
Okay. I don't know. I made up this argument yesterday, so I hope it's correct. Right? So this is not, for example, Hu Xiao. Good. So where do we stand? In particular, I can multiply it again by d. And now you see that, so this must actually be 0, right? So we must have equality in this HR1, right? So now we claim that if we have equality in this HR1, we can apply this lemma 1, right? And what that means is that we can replace gamma 1 by anything we want, right? Right, so that means by lemma 1, right? It really means that d dot alpha dot anything, right? Dot gamma 2, gamma n minus 2 is 0. In particular, I can stick in here if I want an ample divisor. Good? So what I've shown is that if I have equality in the Alexandrov-Fenchel inequality for gamma 1 to gamma n minus 2, right? If alpha is in the kernel of the quadratic form generated by gamma 1 to n minus 2, it's also in the kernel of the quadratic form generated by omega gamma 2 to gamma n minus 2. I could replace one of these guys by an ample divisor. But if I can do it once, I can do it again. So I could just keep doing this until I've replaced all of these guys by ample divisors, right? And then I can apply HL1 because now they're all ample. Right, so if I repeat this, I will get that alpha dot omega to the n minus 2 is 0, which means that by HL1, alpha is 0. That's what I proved, which cannot be right because we know that there are many situations where that's not true. So I cheated you some. But this is the basic argument. So this entire argument I gave here would work when the gammas are all empty. And that's the situation in which Weil was right. Weil was actually trying to basically prove this. That's what he's trying to prove in the case that the gammas are all ample. And this is the way that he did. Is it good? Okay. Now, so I have to explain to you where I cheated, right? Right? If this argument I gave you were correct, we would never be any non-trivial equality cases. Okay? So this cannot be true, so I cheated you some. Now the question is, the problem is the following. What did I do here? I applied HR1. HR1 says that this is greater or equal than that times that. And in particular, when this is positive, right? If this is 0 and this is positive, then that must be 0, right? That's what I used. And then I said, well, you see, all of these divisors are big. It's gamma 1, 2. So if I have gamma D times gamma 1 times gamma 1, gamma 2, this is the intersection number of big divisors, right? And intersection numbers of big divisors are always positive. So that's what's my reasoning for why it should be positive. But this is a nonsensical argument because you see, just because a divisor is big doesn't mean its restriction to D should be big. And that's the problem. The same, what am I really saying? Let me translate this back to convex polytopes. If I have a convex polytope, what it means to be big is that the polytope is full dimension, right? It has dimension n. Right? It doesn't, just the fact that the polytope has dimension n doesn't mean that the faces in the direction, normal direction of the rays of the fan all have to have dimension n. They could have any dimension, right? The dimension of the polytope itself says nothing about the dimension of its faces. If the polytope is ample, that is in fact true. So if the polytope is ample, right? If the polytope is ample, it means that it's strictly convex, right? The support from strictly convex on the fan, that this is true. Then its facet directions are in the rays of the fan, its facets are in dimension. So this argument, the entire argument works if you assume that all these gammas are ample. But when these gammas are Neff, it's simply not true. This Neff property doesn't pass down to restriction to.
Neff does, but big doesn't.
Sorry. Big doesn't pass down to. And therefore, not only can it, but it will, in general, be true that there will be many prime divisors for which D dot gamma 1 dot gamma 1 dot blah, 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 to gamma n minus 2 is equal to 0. And then this argument doesn't work. And that's the fundamental problem. And it's exactly because of that that we see non-trivial equality cases. It means that there are some kind of singularities in the problem, right? There are many directions in which some things vanish, and we cannot divide by them, like we do, for example, over here. So there's some singularities. Is it good?
Sorry.
Yes.
Where did you use the restriction? Was it just in the very last step when you said you wanted to repeat the argument, or?
No, I use the restriction everywhere because I'm applying here HR1 on D, not on X, right? Because, okay, so the prime divisors are not net. So I cannot apply, I cannot apply HR1 like there, right? So these guys are not net. So I have to view this as an intersection on D, not on. Yeah. Does it make sense?
Can you explain again how you replace the alpha with omega in that step when you apply lemma 1? First line is
Lemma 1 says that I can replace it with anything because it just says it's in the kernel.
Oh.
It's in the kernel of the quadratic form.
Ah.
I just plugged in omega
I see.
because I wanted to. Because I wanted to go to the hard Lefschetz. I could have plugged anything else in there. So in fact, in order to prove the general case in the convex, in the toric setting, to prove cases where you don't have big, we don't plug in ample stuff. Plug in other. Good, are we good? All right. So we now come to the kind of crux of the matter. So the problem is that we have many zeros, right? So we would like to show Let me just keep this this line over here. If this line were true, if this line were true, then we could go, right? We could go. But the fact is, this line is simply false. There may be many D's for which this line is false. The kind of main observation here is that, okay, if I give you an alpha in the kernel of Q, right, this doesn't need to be true. However, I have freedom because I want to show that alpha is in this linear span. Right? So if I, for example, don't take alpha, but let's say if I take some element in this linear span and I add it to alpha, it's enough to prove the theorem for that perturbed guy. Right? Because if alpha plus any element in the linear span of these guys is in the linear span, then I've proved the theorem. Right? So I have some degrees of freedom. In order to prove the theorem, I'm allowed to add any linear combination of these prime dividers in the kernel of Q, and I'm good. And the basic observation is that even though this statement over here is not true for alpha, I can always find some element in the linear span of these guys, such that if I perturb alpha by that guy, this statement is true. So let me formalize it. Let alpha be in the kernel of Q. Then there exists an alpha prime in the kernel of Q with the difference between alpha and alpha prime being in the span of this prime divisors in the kernel of Q, such that D dot alpha dot gamma 2 and minus 2 from that's the state. But the point is we have these degrees of freedom. And even though we had some singularities, we had many D's for which gamma 1 dot gamma 1 is equal to 0, and we cannot deduce this from it's not true. Yes.
It was alpha prime.
Prime. Thank you.
But both of them.
Both. So even though this is not true, as stated, I can always perturb my element in the kernel of Q in kind of directions I don't care about. So to make this true. And once I do that, then I can continue with this alpha prime. Right? So now what I can do is I can replace, for example, this alpha prime by an ample guy. Sorry, I can replace now when I put in an alpha prime, I can replace gamma 1 by an ample. Now I can do it again. I may again need to modify alpha prime to alpha double prime, right? And then I can replace gamma 2 by gamma. I do have to do this at most n minus 2 times. Eventually, I have modified alpha n minus 2 times, but always only by elements in this space, right? So that I can apply the Hard-Leclerc theorem. That's the proof of this. So if we have this theorem, I've glossed over very small statements that, of course, when I replace gamma 1 by omega, the definition of Q changes. Right? Now being in the kernel, and I have to be in the kernel, for the next step, I have to be in the kernel of the new Q. But it's very easy to see that if I replace one of the divisors by an ample divisor, then there's always going to be less elements, or there are always going to be less elements in the kernel, right? So it only goes in the right direction.
After you replace alpha with alpha prime, you restrict to D, now it's restricts to big thing.
This I'm not clear. I don't know if that's true. No, I don't think so. This I'm not clear. I'm claiming that I can prove this inequality. I'm not claiming it follows from HR1.
Oh, I see. Uh-huh.
Is it okay?
So you get around the bigness?
Let me prove this first. The proof of this lemma is just linear algebra. It uses two things, HR1 and lemma 1. Okay. And in a kind of magical way that I still don't really have, I mean, I can tell you the intuition we have behind it, but exactly why it works is kind of, there is some kind of miraculous linear algebra. Okay. So the first step is to notice that, okay, I have to show this, I want to prove this, I want to prove that I can find an alpha prime such that this inequality is true for all d. Okay? The first observation is that if I just take d not in the kernel, so I want to prove this condition. Star is this inequality. Okay? The first observation is that if I choose a d that's not in the kernel of Q, then star holds for any alpha prime in Q. So in fact, there's nothing to prove. For elements d that are not in the kernel of Q, there's nothing to prove. Any perturbation I make here will automatically satisfy this. Right? I don't have to make any choice. It's automatic. And why is this true? Well, this is a consequence of HR1. So there's really two cases. One of them is that if E dot gamma 1 dot gamma 1 dot n minus 2, I need 2 gamma 1, is greater than 0, then it follows exactly like a pair. I've already proved it for you, right? This is what I kind of took for granted before, that this would be true if the restriction was there. So then you can just apply this argument, right? HR1 plus HR1 makes it complete. Now suppose this is false, right? So I'm not ruling out that this is false. So it doesn't need to be that they're left in the restriction. But I claim if this is false, I can give some other argument. If d dot gamma 1 n minus 2 equals 0, then what do I do? Now notice that d being not in the kernel of Q is the same as saying that d dot gamma 1 dot gamma n minus 2 is not equal to 0, right? So in particular, it's the same as saying that if I plug an ample guide in here, this is strictly greater. So what I'm going to do is I'm going to choose a constant c so that d dot alpha prime minus c gamma 1 dot omega dot, how many do I need? N minus 2, n minus 1, n. Here I need omega dot gamma 2. I can always do this because you see d dot gamma 1 dot omega dot gamma 2 gamma n minus 2 is positive, right? So whatever the value of this alpha prime, here I've replaced gamma 1 by omega. But whatever the value of this alpha prime, I can always subtract a constant times this so that this is equal to 0, just because I have this being positive. That's what being not in the kernel does. And now I can play this game with HR1 plus HL1 with this guy. Because d dot omega dot gamma 2 to gamma n minus 2, well, why is that positive? This should be opposite. So I want to claim now that d dot omega dot gamma 2 to gamma n minus 2 is positive. Why is that? Well, it's true with omega dot gamma one, right? And I can again apply the perturbation argument on omega to replace omega by anything else, right? So I know that guy is positive. So the argument now is that by HR1 plus HR1, this is showing that D dot alpha prime minus C gamma 1 dot alpha prime minus C gamma 1 dot gamma 2 gamma n minus 2 less or equal 0, which is not what I want to show. I want to show it without this C gamma 1. But remember, I assumed that if I put a gamma 1 here, I get 0. So these C gamma 1s exactly. If I did it correctly, which I have to check for a moment. So certainly with 2 of them, it cancels. Why does it cancel with 1? Cancels with 1 because alpha prime is in the kernel. So alpha prime dot gamma 1 dot gamma 2 to gamma n minus 2, that intersection number is 0 because alpha prime is in the kernel. And gamma 1 dot gamma 1 dot gamma 2 is 0 because that's the case level. So here I've shown you that, you see, so I'm not claiming that the restriction is net. I'm claiming that even if it's not net, you use linear algebra. Now, so what I've shown you is that this guy is true for all D that are not in the kernel of Q. So the choices I have to make, right? I told you I can find an alpha prime so that this is true for all D. But the alpha prime, I only have to choose it to fix the values of D in the kernel of Q. Okay, I think by now we know this by heart. So I claim that to prove the theorem, it's enough to show that there exists an alpha prime of the kind that I'm mentioning over there, such that D dot, you see, I want to choose alpha prime so that I have a set of inequalities, right? The inequalities are very painful, right? Finding a solution to a set of inequalities is very painful. I'm going to turn this into an equality set. I want to solve a system of linear equations. So I claim it's enough to show that there exists alpha prime such that D dot alpha prime dot omega dot gamma 2 gamma n minus 2, omega is always some ample guy, equals it for all D in the kernel So what I'm saying is it's enough. This is a system of linear equations. I want to solve a system of linear equations. But what I really want is a system of linear inequalities, right? But I have a system of linear equations. I replace gamma 1 by omega. So why is this enough? Well, again, it's enough by so let's check. There are two cases. If D dot omega gamma 2 gamma n minus 2 is positive, right? Then this immediately follows again by HR1. Right? Because I can just apply, you see, I can apply HR1 to alpha prime and omega, right? So this equals 0 squared, greater or equal this with alpha prime, that's what I want to prove, times this with omega, omega. So if the guy with omega, omega is positive, this is immediate, right? And if D dot omega dot gamma 2 equals 0, then actually it's not even an inequality, then I even get this with equality. And this will always be equal to 0, just by our usual perturbation argument. Because these omegas are in the ample cone, so they are in the interior. So I can again, let's say I can replace omega by omega plus t times gamma 1, or what do I want? No, I can replace omega by omega plus t times alpha prime, and just take derivatives with respect to alpha. Right? And I'm going to get that with alpha. Okay, getting that equals. It's good. So now comes the magical part. So I want to show, what do I want to show? I want to choose an alpha prime, but how many degrees of freedom do I have? Okay. The only choices I have is I can choose an element in the span, right? Alpha prime is alpha plus an element here in the span of these D's that are in the kernel of Q. Okay. So I only have the number of variables are just basically the coefficients of these guys, right? That are in the kernel of Q. So those are the number of variables. So it's a system of linear equations. I have that many variables. This basically, let's say the number of these, well, I have to say something about that in a moment, but let's pretend there's a finite number, which is of course not true, right? So I have the number of these, that many variables. And how many unknowns I have? Well, I have to check how many equations do I have exactly for D in the kernel of Q. So I have here a system of linear equations with the same number of variables as unknowns. So when we realized this, we thought, well, surely this system of equations must have a solution because it has the same number of variables as unknowns. Of course, that's a silly argument, right? Because that's presuming that all matrices are non-singular. But at least there is some kind of hope. So of course it doesn't work, but what we really need to show, right? This is really a matrix equation, right? There's a matrix that maps basically from this span to that span, and I have to show this matrix is not non-singular. I'm not going to prove this matrix is non-singular, but I'm going to show that this particular system of linear equations has a solution. Is it good? Now I have to slightly modify this. So the problem is there may not be a finite number of these prime divisors that are in the kernel of Q. It may have an infinite number. Actually, in the paper of Hu and Xiao, they proved there's only a finite number, but this really uses some algebraic geometry. So if you know there's a finite number, everything I just said makes sense. However, I'm not exactly sure that this is really necessary because this is a finite dimensional space, right? And I'm only talking about the span. So surely all I need to do is pick a finite number of these guys that are linearly independent, and I'm already done. I could just restrict to those guys. I'm never using, in this part of the argument, I'm only talking about spans. I'm never using positivity. So it's not quite clear to me why you would actually need to know that there's only a finite number. But maybe I'm overlooking something. But in any case, there's just, we're just taking here a finite system of linear equations. So let me remind you, how do we show, suppose, I'm not talking, now let's not think about this system of linear equations, let's think in general. Suppose I have a system of linear equations. A is a symmetric matrix. These are symmetric matrices. They're symmetric quadratic forms because, of course, intersection products don't care about the order, right? So this is a symmetric matrix. Suppose that A is a symmetric matrix, and I want to show that there exists a solution to this system of linear equations. This is what we want to prove. Right? Here, X are the coefficients of those D in the kernel of Q, and AX are exactly those conditions. Is it clear so far what I'm saying?
Let's repeat that. Oh, sorry, you just went fast.
So let me just write let's take the matrix. Let's take a matrix. Here I'm pretending that there's a finite number of these guys, okay? But if there's not, I think it's enough to just pick any set of linearly independent. Let's take this matrix, which is D dot D prime dot omega dot gamma 2, gamma n minus 2, right? Where these guys are in the kernel. So this defines the matrix, assuming that there is a finite number of these in the kernel of Q. Otherwise, I think you just pick a basis. So what do I want to show, right? So alpha prime, what is alpha prime? Alpha prime is alpha plus something in the linear span of these guys, right? So to show is that there exists X, right, a vector X in, let's say, R to the, you know, something like this, assuming it's finite, right? Such that AX, right, so this is indexed by D, is exactly what? Well, it's exactly the vector D dot alpha dot omega. Not alpha prime, alpha. So my alpha prime will be alpha minus some I, some D, XD times D. Right? Does that make sense? So this is just some vector. Let's call this Y. I just have here a system of linear equations. I want to show that there exists a solution. Exists an X. Is it good?
Yeah.
Okay. Now, how do you show that the system of equations has a solution? Well, there's a dual characterization. So also notice that this is self-adjoint. It's a symmetric name. Right? If I swap these two guys, I get the same number. It's an intersection. So when does there exist a solution to a system AX equals Y? That's the same as saying that Y is orthogonal to the kernel of A. For a symmetric matrix, that's the same thing. So it's saying that for all V such that AV equals 0, we have that the inner product of V with Y equals 0. That's the dual characterization of the existence. I've turned an exists into a for all. Is it good? So if I translate this, what do I have to show? I have to show that for all delta in the span the internal Q such that D dot delta dot omega dot gamma 2 gamma n minus 2 is 0 for all D in the kernel of Q. Well, suppose for any delta in the span of the elements of the kernel of Q that satisfies this equals 0 for all of these guys, we also have that delta dot alpha at omega gamma 2. So that's this today. Good. I complain I have to prove this. I have to remind myself how to do it.
Are we still assuming gamma is big? We don't have that.
I will use it in a moment, but in fact, it's not required here. Something much weaker is required. So this statement holds under a much weaker assumption, which is important if you want to go to more general situation. But in a moment, I'm going to use. So far, I haven't used it. Right? So I claim. How am I going to prove this? I claim it follows from HR1 and lemma 1, like everything else that I've said in this. So observe. That delta is in the span of these guys, right? And I have so just by taking linear combination of these, I get delta dot delta dot W equals 0. Right? So far, so good. Now, that's one thing we can observe. Now, another thing we can observe is that if I take gamma 1 dot delta dot W dot gamma 2, gamma n minus 2. This is also 0. Why is it true? Well, this is just because delta is in the kernel of Q. And Q is just a quadratic form generated by gamma 1 and gamma 2 into gamma n minus 2. So this is just because delta is in the kernel of Q. On the other hand, what happens if I take gamma 1 dot W dot gamma 2 gamma n minus 2? This is positive as we assume that all these guys are big. That's why I'm using big. However, we don't need big. We just need all of these kind of guys to be positive. That's a much weaker condition. You can translate this back into a dimension condition that I had before. So far, so good? So we have here another equality case of HR. Okay. Because this squared is equal to that times that. And this is positive. So by lemma 1, what this shows is that delta dot W dot gamma 2 n minus 2. And if I multiply this by alpha, I get this. That's the energy. So somehow or other, again, by using the only properties we ever use, we can prove this dual condition, right? So we're not proving this matrix is non-singular, but we're proving that this system of equations always has a solution. A bit of a miracle too. We knew what we wanted to prove and we proved it. But why exactly it works is not so. Are there any questions?
I've sort of lost where D being prime is being used anywhere.
D being prime is being used because heavily because I'm always assuming that these guys satisfy the Khovanskii-Teissier inequality. But this is not NIF. So I need to be able to interpret this as the intersection number of divisors, of NEF divisors on D. That's where I'm using that. So modulo some like inaccuracies about algebraic geometry, I have proved this here for you in the case of big. See it type. And it's just linear algebra. Now the inaccuracies may be very nasty. If you want to read the authoritative version of this, you look in the paper. Now in my last, let's say 5 minutes or so, let me tell you a little bit about the general. So what happens if you till big? So the problem is that if the divisors aren't big, you're kind of screwed at the very beginning. Because this argument, I mean, forget even about proving this lemma. Okay, so this lemma over here, I only used big and a very. All you need to prove this theorem over here is that all of these intersection numbers are positive. That's a much weaker. You just use the lemma that I showed, lemma 2, about the dimensions. You will give you some dimension conditions on the gamma. And it turns out that these are optimal, these dimension conditions. We understand if those dimension conditions are violated, then something trivial happens, and you can just immediately write back. So this theorem over here really doesn't require it. Where big is really important is in this argument of what, right? Because what we showed is that, right, what did we have? We had some, I don't remember exactly which ones they were, but we had some divisors, let's say n minus 1, and we showed that for all pseudo-effective delta, and we showed that if we multiply them by, I don't remember what I had here. There was a gamma 2, and then I think there was an alpha prime, and a gamma 2, something like this. It doesn't really matter for what I'm going to say here, but let me just make it accurate. There was a D. There were 2 alphas, a gamma 2, and a D. Okay, so there were 2 alphas, There's a 2 here. And a 2. So I have what? N minus 3, N minus 2, N minus 1 dot Z.
Is your removal of singularities there?
Yes. No, we've already applied it. So we know that this is true. Okay. So what we conclude is that, right, as an outcome of the removal of singularities theorem, we know that this is true for all pseudo-effective delta, right? And then we said gamma 1 by construction, gamma 1 dot alpha prime dot gamma 2, gamma n minus 2 equals 0, right? And then, right, this is true just because alpha prime is in the kernel, right? And then I said because gamma 1 is big, I can perturb gamma 1 in any direction, right? It's negative for all delta, pseudo-effective, because gamma 1 is in the interior of the pseudo-effective cone. I can perturb it. This is a maximizer. I can perturb it in any direction, and it just shows that this is. That was the argument. But if gamma 1 is in the boundary of the pseudo-effective cone, this argument simply doesn't work. Not only doesn't it work, but it's simply not true. Okay, what I'm saying. So this idea that I can now say that this being 0 means that this guy is 0, that's just false. So then the question is, then what do you do, right? How do you now work? And in fact, this is not what we do in the convex case. What we try to do is some kind of induction on the dimension. So in the convex setting, we have a beautiful fact, which is related to the question that June asked me before, which is that if I have some mixed volumes of some polytopes, and here I take a one-dimensional segment. I take here a one-dimensional convex body, which is just a line segment, all right. And I multiply this by n. This is equal to the mixed volumes of the projections on the orthogonal, on the hyperplane orthogonal to U of each of these polytopes. Now, what we have here is that in the convex setting, gamma 1 is some polytope. It may be lower dimensional, okay? So it may not be big. It may live in some subspace. So this being 0 doesn't mean that this guy is 0. But more or less what it means is that we can replace this guy by any one-dimensional segment in the subspace spanned by this gamma 1. By the polytope that's going to correspond to this gamma 1. Almost up to a set of measures. And what that means is that even though this guy is not big, we don't actually say that this is 0, so we can't replace it by something ample. But we can show that there are many projections of these other polytopes so that I get an equality case in dimension n-1 for the projections. Once we have that, we can do induction on the dimension, right? Suppose that we have proved the theorem in dimension n-1. Then we have some characterization about the kernel of these for every projection, and then we have to glue together this information of the projections in a different direction. And that requires some argument. But that was, roughly speaking, how we work in the convex geometry. Now, the problem is that I don't know of any analog of this story over here for general algebraic varieties. It would be really nice to have. I don't even know how to describe this procedure so well. Even in the toric case, it's not so clear to me what is the correct way of thinking about this very natural convex geometric fact in an algebraic geometry set. So in the absence of such an understanding, you need to find some other way around. So let me tell you kind of the general picture. So first of all, we need to know what is true. So the conclusion of the main theorem in the case of big, right? So this conclusion doesn't actually require the divisors to be big. It remains valid in the supercritical case. And the supercritical case is the case where the dimension of gamma I1 plus gamma ik is greater or equal k plus 2 for all k. And this kind of condition should now look familiar to you, right? I mean, these are the kind of dimension conditions we expect when talking about positivity of intersection numbers. Here, right, greater or equal than k is necessary to have a non-trivial fact, but here I have plus 2. Well, everything is just 2 dimensions larger than it needs to be just not 0 all the time. And this is, we call this the supercritical case. And it turns out in this case, you see, none of the divisors have to be big. This could be true even if none of the gammas are big. Not only can this be true, but in fact, in applications, if you look, for example, on Stanley's inequalities for partially ordered sets, these are applications to combinatorics of the mixed volumes. And in these situations, the divisors are never big. None of the divisors are big. So in fact, the situation where everything is big is, of course, the first case you want to understand, but it's not the case that shows up naturally in some sense in many applications. Like you almost always live on the boundary of this. So under such a situation, it turns out the answer is correct. Okay, the same answer holds, but we don't know how to prove this. Even this, we don't know how to prove in algebraic array. Otherwise, actually, there's a complicated picture. There's a whole other class of equality cases that happens when this condition fails. And these, I mean, I don't have time to describe it, but there are many more equality cases. That's one of the hardest parts of in the toric case, this is one of the hardest parts of the paper to understand these. But at the very least, this assumption does hold in many applications. The supercritical assumption is very natural. It holds in many applications. And in the algebraic geometry setting, this remains open even in this. What Hu and Xiao prove is a weakening of the fact that they're big. What they prove is if you assume gamma 1 is big, so has dimension n. Gamma 2 has dimension at least n minus 1. Gamma 3 has at least dimension n minus 2. Gamma 4 has at least dimension n minus 3, etc. It's a much stronger condition than this. That's also not true in any application, I know. But it's weaker than what we do here. And the way they do it is also by induction on dimension, but not in this way. What they do is they take this gamma 1. If gamma 1 is big, they can take some generic hyperplane section and pass down to some n minus 1 dimensional variety. And because gamma 1 is big, you can use the Lefschetz hyperplane theorem to paste together the information that lives on those projections. Now, once you did that, because gamma 2 is at least n minus 1 dimensional, once you intersect it with this generic section, it's still n minus 1 dimensional, so it becomes big on that guy. And you can iterate the argument. So somehow or other, what they need, they can use positivity in algebraic geometry, but they always need in every step of the induction, one of the divisors to be big. And somehow the problem is that when no divisors are big, there's not enough understanding of positivity. There's some kind of lack of understanding of positivity in algebraic geometry to have some form of induction dimension that works in that situation. And that's really at the core of I think at some level, that's the core of the difficulty here. It's not an area that I understand, but it lies at the core of why you asked me at the beginning, why has this not been extended further? And I think these kind of questions really like it all. But I definitely believe it should be true, that the complete analog of what we have here should be true in a very general sense. Don't know. Let me end there. Thank you.
If all the gamma i's are equal, does the argument, is there some trivial version for to prove this?
Well, it's certainly in the convex geometry, it's much easier when all the gammas are equal, but I'm not sure whether this argument particularly simplifies. So the thing is, when all the gammas are equal, there are only two non-trivial cases. All the gammas are equal. The one case is when the gamma is big. In this case, the argument works as I wrote it. And if gamma has dimension n minus 1, then you're already in this situation. And I don't know. I don't think even that case has been solved in the algebraic geometry set, but I certainly have to try. I think understanding the supercritical cases is by far the most interesting. There is an elementary fact, I should just say, it's just an elementary fact about dimensions, which you can check from the dimension characterization. And if you look at these kind, if alpha and beta are nef, and you look at these kind of sequences, they show up very often, right? They're log-concave by the Khovanskii-Teissier Inequality. And you ask for equality cases here, then the only non-trivial equality cases are always supercritical. You will only see these critical equality cases if you have more than two. If you have more than two divisors in your intersection. So because these are coming up so often, the supercritical case is really very, very common. So I think those are, in some sense, the most interesting cases. But yeah, it's a good question. If all of the divisors are the same and they have dimension n-1, so it turns out in the complex geometry setting, that case is particularly easy, because in that case, you can write formulas for everything and everything becomes completely trivial. And something factors. I don't remember exactly, but I can reconstruct this. But I don't know whether some analog of that is true in general. That's a good question. Would be a good model problem for these.
Is there a statement like this for Lorentzian polynomials?
So, good question. Let me tell you something about Lorentzian polynomials that I think is a statement like this for Lorentzian polynomials is completely vacuous. The reason that this is a difficult problem is because in algebraic geometry you have two cones. You have the pseudo-effective cone and you have the nef cone, and they one sits strictly inside the other. And it's the discrepancy between those two cones that is causing all this rich behavior that we see here. If you have a vanilla Lorentzian polynomial in the usual sense, there is only one cone, which is the positive cone. And then everything is trivial. If big means now that you are in the interior of the pseudo-effective cone, then you're ample. Then everything is trivial. And so there's nothing to prove. So the big case is not interesting. So in some sense, we can say some easy things in the Lorentzian case. But something really useful, I don't think I can write down more formulas, but I don't think I can give in 1 minute an adequate answer to this. But in some sense, Lorentzian polynomials is a very poor theory because you only have one cone. If you take Lorentzian polynomials on cones or something like this, then of course you can reproduce all of this business.
Yeah, there are setups,
Exactly.
Lorentzian fans, where you do really have two different cones.
So in the paper of Hu and Xiao, they I believe proved this theorem for Lorentzian fans under some assumptions which I don't remember off the top of my head. So everything I told you will go through if you have this kind of algebraic set.
Something like the existence of such a thing as a prime divisor.
I mean, all you really need is HR1 and lemma 1. I mean, anything that will allow you to do this basically will allow you to reproduce the statement for big, right? But again, we lack a very good understanding of what happens beyond that. There's another thing I would like to say about Lorentzian polynomials, which is that in a sense, what we try to do is induction in dimension. Now, what does it mean to go to lower dimension? Well, in a Lorentzian polynomial, it just means that you would plug in some coordinate vectors into some of the slots, right? If I I never think of Lorentzian polynomials. I always think of them as being polarized because then they look like mixed volumes. So if you polarize a Lorentzian polynomial, you plug in coordinate directions in some of the slots. This is like passing to lower dimension. So the problem is that in all of these situations, in convex geometry, in algebraic geometry, if you're in dimension 2, you don't have any non-trivial equality cases. But in Lorentzian polynomials, if I plug in, if I have a Lorentzian polynomial of degree 2, you may still have non-trivial equality cases. And so if that happens, in fact, it often happens. And if that happens, then those non-trivial equality cases in dimension 2 should somehow propagate through. And that also we do not quite understand how to do. So I would say for Lorentzian polynomials, it's not quite clear exactly how to even formulate. You can make some statement about Lorentzian fans, and then you have the exact analog of this, including big. I think I have to double check. But for general Lorentzian polynomials, but I think it's a very interesting question. Pick your favorite setting. Let's say, the generating polynomial of a matrix or something like this, and try to ask the same questions. And now it's very concrete, right? And one might hope to do something. We have attempted not yet fully succeeded in pushing it. Yes.
So when you say like in poset theory, the divisors are never enough, what is a divisor in poset theory?
No, this is just standard toric. There is this inequality of Stanley, which says that if you have a poset, right, and you fix some element in the poset, and now you look at these numbers nk, which is the number of linear extension f, right, from P to whatever the size of n, such that fx equals I. And so these numbers are log-concave. This is one of the first log-concavity inequalities. I mean, one of the first is from 1981. It's one of the first examples of this kind of phenomenon that is described by these Lorentzian polynomials. And the way he proved that is just to realize that nk is equal to n minus 1 factorial times the mixed volume of some polytopes. Q R, where these are repeated k minus 1 times, and these are repeated these are n minus 1 dimensional polytopes. So he just cooked up some polytopes. They're related to the order polytope. The order polytope of this P. Okay? And basically what you do is you take these polytopes and you take some slice of them determined by the direction x. I have to remind myself the exact definition. But if you just look at this construction, you look at these polytopes, in no interesting case are either of these polytopes full dimension. If one of these polytopes is full dimensional, then you have some trivial poset or something like that.
Interesting.
So in basically any interesting situation, both of these polytopes have dimension less than n. On the other hand, this situation, you're exactly here. So you're always supercritical. So to understand the equality cases of these guys, you only need to understand the supercritical equality. And we did it. So we applied this theorem in the supercritical case to this guy. That gave us some statement that the support function of Q minus a multiple support function of R, right, has this property that it's a linear combination of these guys, which has to do with the dimensions of the faces. And then we had to do some work, because now we know something about the dimensions of the faces of these order-like polytopes. And we had to translate that geometric information back to combinatorial information about the poset, and this required some problem-specific arguments, right? But that's how you can find equality cases of combinatorial. In principle, if you had such a theory in a more general setting, you would hope to have a machine like this that allows you to understand when you have geometric progressions in log cases. But in my experience, I've never seen such an inequality, at least you have Stanley's inequalities and their derivatives, which are the most kind of classical ones. They are never nothing is ever big. So it is genuinely of interest to go beyond big. That's not a technical.
Okay, let's thank one.